So today we're looking at different representations of exponential functions. So we're going to be looking through different ways to create equations, to deal with situations, tables, and graphs, and just kind of different ways that these would relate to each other. So we're going to start by actually taking a little bit of a step back and thinking about some of the connections we made back when we were talking about the bounce height, so the bouncy ball lab. So Arnold dropped a ball during the bouncing ball activity and recorded its height in a table. Part of his table is shown at right. What was the rebound ratio of the ball, and what height did he drop the ball? Write an equation that represents his data and explain your equation. So as we learned back when we were doing the bouncy ball lab, the multiplier as you move from one point to the next should be approximately the same. So you should be able to calculate the rebound ratio by taking the third number divided by the second number, or the fourth number divided by the third number, and whatever decimal we get is what we would need to multiply by to move forward. So in my calculator, I'm going to do 67.6 divided by 84.5, and that gets me 0.8. So what that means is if I were to take 84.5 times 0.8, that'll get me here. And if I take this times 0.8, I should get 54.1. Which I do. I get 54.08 or 54.1. Now the question is, how do I work that backwards then? And just like when we were learning about inverse operations, since I know moving forward I need to multiply by 0.08, in order for me to be able to go backwards, I would just need to unmultiply or divide, because that's the inverse operation, in order to get my previous number. So I can take 84.5 and divide by 0.8 to get 105.6, and then I can divide by 0.8 again, and that gives me 132. So that fills in our table for us. So again, I got my number, or I figured out my rebound ratio moving forward was multiplying by 0.8. So to go backwards, I ended up dividing by 0.8. So my rebound ratio is 0.8. And in order to write our equation, what we've been talking about over the last chapter and the beginning of this chapter is that it's going to have that t of n, or y equals your starting value. So back when we did t of n, we said t of n, and it was our initial value times your multiplier to the n power. So our initial value would be our drop height. In this case, that would be 132 centimeters. Times our multiplier, which would be our ratio, what we're multiplying by to get from number to number. Then I'm using y and x in this particular case, but you could use t of n and n. And that's how we end up with our equation. So that's what we were doing last chapter with our sequences. We're actually taking that very similar idea, and hopefully you see just how similar those ideas are, and we're going to be dealing with equations this time. So let's look at 20B. A major tech company, Expo Grow, is growing incredibly fast. The latest prospectus, the report on the company, said that so far the number of employees Y could be found with the equation Y equals 3 times 4 to the X power, where X represents the number of years since the company was founded. How many people founded the company, and how will the growth of this company be described? So keep in mind that founders would mean we're talking about year 0, so they're asking you to plug in 0 for X. Now, you might already know what's going to happen. You might need a calculator for this either way. But I'm going to plug in 0 for x. So I'm saying 3 times 4 to the 0th power. And I remember from my rules of exponents earlier this year that anything to the 0th power is just 1. So this really says 3 times 1. That would mean that at 0 years, there were 3 founders. Conveniently, that appears to be my number out front here, which matches with what we learned when we were doing sequences. I wonder, this is saying up here the multiplier is what came next. This appears to be in the same place, meaning that 4 should be our multiplier. But we can test that out by just plugging in 1 for x and seeing if we did end up actually multiplying by 4 to get from number to number. So when we plugged in 0, we got out 3. If I plug in 1, I would get 4 to the first power, which is 4. So 3 times 4 is 12. And I do see, in fact, a growth factor of 4. So that would mean this is coming from that spot. So that's kind of nice. That tells us that what we learned in sequences, that setup, is going to be very similar now that we've moved into equations. The only difference is we might see a little bit of change in what letters we're using, but otherwise the setup is basically the same. So part C moves into an equation of computer virus. It says a computer virus is affecting the technology center in such a way that each day a certain portion of virus-free computers is infected. The number of virus-free computers is recorded in the table at right. How many computers are in the technology center, and what portion of virus-free computers are infected each day? How many computers will remain virus-free at the end of the third day? So, 3 different questions that they're asking here. We figured out in part B that the setup is basically the same as what we learned in sequences. So this first number is going to tell us like our initial value. So looking at our table, I can find my initial value by looking at wherever x was 0. So just like up here where I plugged in 0 to find my initial value, here I can just look at my table and see when 0 is plugged in, my initial value is 27. So there are 27 computers in the lab. Now to find my multiplier, this number, which we said was the same as what we had in sequences, I need to figure out what's the pattern. What am I doing to get from number to number to number? Which conveniently, we did up here originally as well. So I can use what we did up here. So in order to find my 0.8, I did my third number divided by my second number. Down here, I'm going to do basically the same thing. I'm going to take my number that I have for 1 and divide by my number I have for 0. So 18 divided by 27. And I get a really long decimal, but I'm going to write it as a fraction of 2/3. So 27 times 2/3 should get me 18. And then 18 times 2/3 should get me 12, which it does. Now, they ask us kind of or they are very specific about this. They say what portion of virus-free computers is infected each day. So this is how many computers are uninfected. So then the infected rate would be only 1/3 of them are getting infected each day. So they worded that kind of funky. They ask what portion of virus-free computers is infected each day. But this is actually referencing the uninfected computers. Then finally, they want to know how many computers will remain virus-free at the end of the third day. That's looking for us to multiply by 2/3 to get to our next number.